got to picture this happening in stars, okay? The alpha particles, somehow in this process, alpha particles are either emitted or they're building up by alphas. But what I noticed was a trend here. 100% of the isotopes that you find for a sodium atom anywhere in the universe, because of its stability rules, I would have to imagine, 11 protons, 11 neutrons. 11 protons, 12 neutrons. This sticks together. 11 protons, 13 neutrons. Doesn't stick together. Sodium with a mass of 23 is going to have 11 protons, 12 neutrons every single time. You will never, I guarantee, you can search every sodium atom in this universe, and if you find any that are stable with more than 12 neutrons or less than 12 neutrons, I'll pay you $1 million space bucks. Anyway, what I noticed from the chart here, from sodium to aluminum, this is an alpha particle away. Add another alpha particle. Aluminum with 4 mass, 27 to 31. Phosphorus. The only isotope that you find of phosphorus, any phosphorus atom, isotope is that one number of neutrons. 16 neutrons. The only one you'll find. Aluminum, same thing. There's one isotope, one nuclide. There's so many different names for the same thing. They're talking about the atom nucleus. The number of protons doesn't even come into play, because if you change the number of protons, you're changing the name of the element. These are the elements that we're talking about, so they have to have 13 protons. That's an aluminum. But when you look at the number of neutrons, only 14. When you look at other elements here, magnesium with 12 protons, well, there's one isotope, nuclide, that has 12 neutrons, 12 and 12. The most abundant isotope, nuclide of magnesium you're going to find is going to have a mass of 24, because it's going to have 12 protons and 12 neutrons. But in any sample, even in space off an asteroid, you're going to find some other isotopes of magnesium, and one's going to have 13 neutrons, the other's going to have 14 in pretty much even amounts. And this is why I drew this table. It's the only one I've seen of this way, the chart, I guess I'll call it. It's not a table. I knew that before I started. I said, don't call it a table. It's a chart. The chart is listing the isotopes that exist in nature with the size representative of their abundance. All the other tables have the boxes the same size. So aluminum, see how it's big? There's only one isotope, and that's why it gets the biggest box. Magnesium, this isotope with 12 neutrons is twice as much as there is with the 13, so the box is bigger. When you look, you'll see which are more abundant. Silicon 28, 14 neutrons. Well, there's an isotope that has 15. There's an isotope that has 16. But most of the ones you find are going to be 14 and 14. Now, do you notice something that should be obvious even to a third grader? These are even numbers. Remember, especially the oxygen, 8 protons, 8 neutrons. Put my periodic table t-shirt down here. The elements that are making these. Even numbers. Carbon, 12, had 6 protons, 6 neutrons. Oxygen, 8 protons, 8 neutrons. Neon, almost all the isotopes of neon, 10 protons, 10 electrons, 10 neutrons. The atom would have that. So we're going to keep this informal here. I don't like it being too stuffy. I'm going to walk off camera, grab my coffee here. So are you looking at the chart here? We have our hand. We're going to come up here. Exactly an alpha particle up from the phosphorus. Get phosphorus in there. See phosphorus down the corner there? Phosphorus with an alpha goes to a chlorine, but check it out. Chlorine splits. Half of the isotopes of chlorine that you find, odd number protons, 17. Even number neutrons gives it an overall mass because the neutron and the proton are roughly the same weight, same mass. 17 and 18, 35, odd number. 50% of the other ones you find are going to be 17. Next number would be 19, right? No, 17 and 20. Gives us an overall odd number again, 37. That's a prime number too, isn't it? Love them prime numbers. So the two isotopes that you find of chlorine, any atom in the universe, any sampling, if you get two chlorine atoms, the chances are one is going to be this isotope, 18 neutrons, the other, 20 neutrons. The only two you'll find. So when we were talking about trends before where it was even, 2 neutrons, 2 protons, helium-4 alpha particle. 6 protons, 6 neutrons, carbon 12. Oxygen, 8 and 8. We'll talk about magic numbers next time. When we come up after calcium here, we're going to see again 39 mass for potassium, 19 protons. It's got to be a calcium atom if it's got 19 protons. Above 19 is 20. 20, 20. You see 20, 20? Carbon sees that 10 protons and 10 neutrons is what's doubly magic, they'll call it. Very stable isotope. You'll find from stars fusing calcium, 20. Now remember, 20 protons, always a calcium atom. 20 neutrons, stable. 21 doesn't exist. 22 doesn't exist. When you get down here, though, to calcium with a mass of 46, this has a magic number of 26. So this is doubly magic also. So what you find, the two most abundant isotopes of calcium are the 40 and the 46. 26 neutrons, 20 neutrons. So what you see is a stability thing. 20, notice there's some elements here. 20 neutrons. They're going to call that a magic number. 20 protons. There's all these isotopes of calcium in there. But the trends I was showing was things that nobody else seems to notice. When we look at our 100% abundances, as I was talking about before, we get back to this here. Metals turn out to be really cool elements. All the enzymes in your body are using these metal ionic complexes in the middle. Photosynthesis, magnesium, our glycolysis, all these elements, okay? Cobalt, 27. Iron, 26. Nickel, 28. These three elements are at the peak of what they call a binding energy curve graph plot. Anything above this takes energy to fuse them together. They say that stars won't do that. That's when they'll start to stop fusing and let gravity take over, and then the gravity will crush them enough that they'll supernova, is the modern theory of that. But what happens actually is that the atmosphere of these stars, if there's neutrons available, will start adding to the nucleus and make elements beyond that. So the supernova theory holds for a general accounting of the averages of these masses, okay? So remember the other trend we were talking about on a periodic table, iron, cobalt, nickel. These elements are the highest that stars will make by liberating energy freely, let's call it. So as we look through, we're going to get back to our 100% isotopes, as we called it.